All right. So here we go for 11.3. So in our previous section, we were talking about arithmetic sequences, where we sort of added the same number every single time, okay? And as nice as that was sort of as a warm-up for our brains, what we're really looking to do is look for different kinds of patterns that are maybe a little bit more applicable in our real lives or our future applications, whatever it is that we might choose to study, okay? And so let's take a look at these series of dots, okay? So at 1 minute, how many dots are there? 6. So using our previous notation, we can say that a sub 1 equals 6, all right? How many dots are there in the second minute or at 2 minutes? Yeah, looks like we have 12. Okay. What about a sub 3? How many dots there? And a sub 4? Good. All right. So even from these numbers, 6, 12, 24, 48, I think we can tell a few things. One, we are no longer adding the same number every time. We're not subtracting it either. What is happening here? We are doubling. Excellent. Ashley, I love the way you said that. We are times 2. We're multiplying by 2. Okay? So what that means for part A is if I were to describe this pattern, I would say the number of dots at minute 1 is 6. And we know we said that's our a sub 1, right? We're using our fancy grown-up notation. Then, in order to find the number of dots at any time, we multiply 2 to the number of dots in the previous minute. Okay? Well, what we have here is actually the start of our information we would need for a recursive formula. Okay? So if we were to write a recursive formula here, remember, that's the one that's not quite so useful, but is easy to write an equation for. We would say we want to start at 6. That's the first part of it. And then we would say to get any term, a sub n, we're going to take 2 and multiply the previous term, a sub n minus 1. Okay, so this is our idea for the recursive formula. We tell someone how to start, we tell someone how to get to the next term, and then we leave it up to them to kind of finish that pattern. Okay, so you take 6 times 2 times 2 times 2 times 2 until we get to whatever number we want. Okay? All right, so how many dots do we think there are going to be in 10 at 10 minutes? Or we could think about that as asking, what is a sub 10? Right, so I could kind of just keep multiplying, right? I could just do 48 times 2, and then that times 2, and then that times 2, and then that times 2. But that gets tiresome after a while, right? So the recursive formula might be good for the first few terms, but when we go beyond that, we're really trying to say, we hope there's an explicit formula, okay? So our explicit formula for geometric sequences look something like this. A sub n equals a sub 1 times r to the n minus 1. Okay. Now, this r, okay, let's make a note of this. R equals not the common difference, but something we call a common ratio. Okay, so the common ratio is just what number are you multiplying by to get to the next term. And so if we take this formula, a sub 10, then we want to plug in 6 for our a sub 1 times 2 to the 10 minus 1 power. Okay, well, a sub 10 equals 6 times 2 to the 9th. And if we remember our order of operations, we do 2 to the 9th first, and then we multiply by 6. We should get 3,072 dots at 10 minutes. Okay. All right. How do we modify our setup here to find out when there will be that many dots? Yeah, exactly. So we're going to take our explicit formula, a sub n equals a sub 1 r to the n minus 1. And instead of plugging in that big number for the n, that is actually how many dots. All right, how do I solve for n? That's a good first step here. It is very, very similar to our first unit, folks. Yes, indeed. Okay, but this 6 is attached to this other thing by multiplication, right? So yeah, we should move the 6, but let's divide by it. Good. Okay. So when we divide by 6, we will get 32768 equals 2 to the n minus 1. Oh shoot. Those exponential functions coming back. We 100% need to use logs to solve this, okay? Here we go. Log base 2 of 32768 equals n minus 1. All right, so we gotta freshen up on those. Like, where do we put what for our logs? This is our base that goes there. This is our number, so that becomes the thing being logged. And then our exponent logs or how we get that thing out of the exponent, okay? So we put this into the calculator. Log 32768 over log 2. That turns into 15. And so n equals 16. So in 16 minutes, we're going to end up with that many dots, 196,608 dots, okay? All right, so a good kind of warm up to think about what happens when we're multiplying by numbers instead of adding by number. But just like we had a definition for the arithmetic sequences, I want to talk about a definition for the geometric sequences, okay? These say nothing new that we didn't see in our previous page, okay? Where sometimes we have a sequence and instead of adding something, we multiply by that something. And so that something we multiply by is called the common ratio, right? And an easy way to find that, you can take the next term and divide it by the previous term, and that will give you your common ratio. Okay? Now, this one is what we consider our explicit formula for geometric sequences. Okay. And that's going to be the one that we primarily use. The other one is good for reference. Okay. But all the things that we talked about before, the notation is still the same. A sub 1 is our first term. A sub n is any term. If someone says a sub n minus 1, what do they mean? Previous term, good. And if someone says a sub n plus 1, they mean the next term. Okay. So we've got our previous term, we've got our next term, and the one new thing or different thing is that this is not a common difference, but a common ratio. Okay. Now, if we think again about what this might be similar to, all right, geometric sequences are not so secretly anymore because cat's out of the bag, but geometric sequences are similar to exponential functions. Okay? And if we think about a graph for a geometric sequence, we'd really have a situation where you have like one, another one, and another one, and another one. So it does go up much more quickly than a linear function. It should look a lot like that exponential growth, okay? Now, if we're cutting things in half instead of multiplying by 2, we're going to get like an exponential decay sort of situation. Okay? But just to kind of frame it in terms of how it's similar to things you already know, a geometric is similar to an exponential function, whereas an arithmetic is similar to a linear function. Okay. All right. Let's do this. Okay, let's do this. I'm going to put you in breakout rooms just for a couple minutes real quick. And I'd like you in your groups to work through examples 1, 2, and 3. Okay? So give those a go. We'll check those over when you come back.